12.
You have a tattoo.
It's okay. I know, it's a tattoo. I have a friend that just got a big old tattoo, his whole forearm. You know what he got?
What?
The tattoo flu.
What's that?
A lot of times your body has a reaction to a tattoo, and it's called the tattoo flu.
Oh, yeah.
So,
What's the symptoms?
flu-like symptoms.
Wait, who got our tattoo?
One of my friends.
Who died?
No, they just have flu-like
Your body,
symptoms.
like, takes it as, like, a sickness.
Yeah, I think it was the axe from Lord of the Rings. That's pretty cool. Pretty cool. All right. I will probably not get a tattoo.
With the chemical foundation.
All right, here we go. This is much better. This fits a lot better this way. A special type of equation that includes heat is called a what equation? Thermochemical. Remember, thermodynamics is what we just finished, Unit 9. You're in an AP chemistry class, the teacher asks you to hold a beaker of water. She drops a cube of sodium hydroxide in the water. To your surprise and utter fascination, you feel the beaker warm up.
No way.
Write the balanced equation, including heat where appropriate. So I would have NaOH plus what? What did I put it in?
Water.
Water. Yields what? NaOH is a what type of base? Strong. So that's going to completely Na plus OH minus plus what? Heat. Heat.
I think we missed a blank.
We missed blank? Yeah. Where? Oh. In a blank reaction, the word heat would be written as a reactant. Endothermic. Endothermic. Describe the difference between system and surroundings. So I would say system is equal to, let's say, the reaction. And then how would you describe surroundings? Don't overthink this. Surroundings is what? Everything else, right? Everything else, or how this reaction is affecting everything else. The above reaction is endothermic or exothermic. This one. Exothermic. The system has lost energy. The surroundings have gained energy. If the addition of heat is required, that reaction is endothermic. Breaking bonds is a... It takes energy to break the bonds. It's endothermic, right? Forming the bonds is exothermic. This is important to talk about. Why would forming bonds be exothermic? When you form a bond, you're releasing energy. Why? Because you are becoming more what? More stable. So don't get those flipped up on the AP test. Consider the following reaction. AB plus C yields AC plus B. The strength of the AB bond is 3 times greater than the AC bond. Therefore, this reaction is endothermic or exothermic. Remember, when you're doing bonds, it's bonds broken minus bonds formed. This is the only one that is reactants minus products. So knowing that, is this endothermic or exothermic? Endothermic, right? Because I'm going to have a larger number on the left than the right. Okay. Data shows only 12 to 30% of energy from fuel put into gasoline-powered car is converted into actual work of moving down the road. What do you suppose happens to 80 to 70% of energy? Where did it go? Heat. Or noise. All right, but most of it was lost to heat. Where is that going? To the... Heat is going to the surroundings. Heat is going to the surroundings. Flip that page. Flip that page. Flip that, move that bus.
What?
That's old.
Move that bus?
Yeah, they used to do Extreme Home Makeover on when I was younger, and then they would hide the new house. They'd put the big tour bus in front of it, and they'd be like, move that bus, and the bus would go and you'd see their new house.
Fixer Upper not. Of course, Derek.
No, actually Fixer Upper was after that.
But this is no Derek show.
All right. Here we go. Study the energy diagram for the reaction. DE plus F yields DF plus E. Use the information in the diagram to answer the following questions. What is the approximate potential energy of the reactants? What would you guys say?
30, yes.
Yeah, 30 kilojoules. How do I know? Just look. All right. What's the approximate potential energy of the products? 10 kilojoules. What is the overall change in energy of this reaction? What kind of 20?
Negative.
Negative 20 kilojoules. So the reaction, therefore, is exothermic, and it is losing energy. Good. Down here. During photosynthesis, light from the sun is used to convert carbon dioxide into water and oxygen. Carbon dioxide and water and oxygen. The high energy molecule glucose, C6H12O6. Sketch an energy diagram in the box to the right showing this process. Include the products and reactants on the diagram. So let's draw our thing. Kind of looks like this. So I have CO2 plus H2O. And then I am making O2 plus C6H12O6. Why are we talking about photosynthesis at the end of chemistry? I don't know. Also, where's my sunlight gonna go? That's the activation energy, right? The sunlight helps me get over that hump, right? Is this change in energy positive or negative? Positive. Is photosynthesis endothermic or exothermic? Endothermic. Complete the table for each of the following physical changes. Energy lost or gained. Water vaporizes.
Lost.
In order to make water evaporate, you have to put energy in. Water freezes. Lost.
Did you say that bonds? Oh, okay.
Water condenses. Lost. Right? Endo or exothermic? Endo. Exo. Exo. Flip the page. We're cruising. We're dancing and singing and moving to the grooving. And just when... What'd you say? Play that funkin'. We are. You're making hard-boiled eggs. Funny story about hard-boiled eggs. So we had a pack of 24 eggs. We had 16 eggs left. So we did 12 out of the 16 eggs hard-boiled to color for Easter. And I told my wife, the 12 on the right are the hard-boiled eggs. So don't use the 4 on the left. Or maybe, I don't know, the 9 on the left, where it was maybe did 12. 9 on the right were hard-boiled, the 3 on the left were not. So we start coloring our eggs, and then I realized we started on the left. So we colored literally 9 hard-boiled and 3 raw eggs. So we didn't know, so it was like egg roulette. But how do you know if one's wrong? You could shake it. The floating didn't work. Just spin it. Because if you spin it, a cooked egg spins nice, right? But a liquid egg is kind of wobbly. You could tell immediately. So it's kind of cool. Yeah. Just science. So here we go. Consider the heat transfer for each step along the way. Complete the chart. What part of the system is gaining or losing heat? Wow. Heat loss, burner. So from the burner, it's going to go into the what? Pan. Right? Burner going to the pan. Pan of water is placed in the hard burner. 2 thermometers placed in the water. Heat is lost from the water. It's going into the thermo. Do we have to keep going on this? Okay. When heat is applied to a solution, the particles blank in kinetic energy. Increase. As this change occurs, the particles blank energy with a solution. Exchange or transfer. I like that. In the solution, in the direction of blank to blank. Hot to cold. Until all particles reach the same temperature and achieve what? Thermal equilibrium. Yes. Equilibrium. Box A and box B contain the same gas molecule. Which box is at a higher temperature? How do you know? B. Because a higher average kinetic energy. Yes. Molecules in which box? Oh, we just answered both. Okay. Explain what would happen if the molecules of box A or B were mixed together. Use the words collide and energy. What would happen?
Molecules will collide.
collide until thermal equilibrium, right, is reached. I guess that's not the best way to write that. They would still be colliding, right? I guess we could say they're colliding and they would transfer energy, right, while still colliding until thermal equilibrium is reached. Cool? Okay. When two objects have reached thermal equilibrium, all of their molecules have the same or the same average kinetic energy, and their temperatures are what? Which one? The same or the same average? The same average. And their temperatures are the same. Because you're never going to have all particles moving at exactly the same temperature, unless you somehow got it to absolute zero. Then you got a Bose-Einstein condensate, and it's really cool. Kind of cool. All right, flip it. Are both the teams remaining still are all the way good till Sunday?
I am.
So you got and you have not gotten. Okay.
People coming out.
The people coming after you got? Okay. Why you got that smirk on your face?
I'm just walking. Wait, so you're like good for the rest of the week?
Okay. You have two blocks of substance. Substance A,
I'm waiting for you guys.
one that is 10 grams and one that is 100 grams. The specific heat of the 10-gram block is higher or lower than the 100-gram block, or the same.
It's the same substance, that's the same.
It's the same. If you have aluminum and aluminum, right, it's going to be the same specific heat. Now, would the energy transfer be the same? No. 1,000 joules of heat are applied to both blocks. Which block will experience a greater temperature change? Q equals SMAT, right? So Q equals, right? We're really solving for a change of triangle T, right? Triangle T equals Q over SM. So which one is going to experience the greater temperature change? The 10 grams, right? Because it's smaller. Okay. Consider two substances, C and D. Substance C has a specific heat of 3.4. Substance D has a specific heat of 1.5. Same amount of heat to both. Which will experience a greater temperature change? Substance C or D? Substance D. Because we know a lower specific heat means it can do what more easily? Change temperature. A lower specific heat, I'm not going to show the math. A lower specific heat equals a better conductor. Right? You guys agree with that statement? Okay. How is the change in temperature calculated? Triangle T equals TF minus TI. How is it possible for the quantity of heat to be negative? Okay. If it's absorbed, it's going to be positive. If it's going to be exothermic, it's going to be negative. So let's just write that down. Absorbed, positive, released, negative. What are the generally accepted units for specific heat? What units do we usually use for this? Joules per gram degree Celsius. Or it could be joules per gram. What would be the same thing technically? Kelvin. Because 1 degree Celsius is 1 Kelvin. Cool. What?
What?
Okay. In the chemistry lab today.
I was just saying Uno Kelvin, that's all I said.
Oh, okay.
Sorry guys. Small spin.
It's all good. In the chemistry lab today,
Basic.
you perform the reaction A plus B yields C. The initial temperature of A and B was 30, when the final temperature of C was 15, which is a loss of energy. Does this disprove the first law of thermodynamics? Where did the energy go? What happened? Yes or no? Does it disprove that energy cannot be created or destroyed? No. Where did it go? To the surroundings. Energy went to the surroundings. In the chemistry lab today, you perform the reaction D plus F yields G. The initial temperature of D and F was 20, while the final temperature of C was 50. Does this just disprove? No. Energy was transferred to the what? The system. Or the substance, however you would like to say that. Flip the page. We're cranking. Like, we are actually locked, yes.
I think if you took
What's the question?
If you took the AP test.
Yes.
You think you'd get a 5 on it?
Yes.
I would hope he'd get is that.
You wouldn't even be nervous about
You would
it?
get a
No.
10, actually.
To get a 5, you only have to get like an 80%. You don't think I could get? You don't think I could get an 80%?
No, I think you could.
So why'd you ask the
You'd
question?
be like nervous.
No.
Do you think you would get like a 98?
I think I would probably get.
I guess if you ran out of time, maybe.
I will say
I meant like perfect.
the only way I would really know, because I haven't taken one recently, would be after the AP grading when like you're going over things. Like last year, I was like, yep, because they go over every question. The question leader's like, here's what we saw, here's what we did, and there was like literally no surprises to me. I feel like I'd probably get maybe miss a point.
Are you kidding me?
Yeah, and it'd probably be on multiple choice.
Do you think if it's like, because you've like graded them, you know how you could answer them to get the correct points?
You guys know how to answer them to get the correct points. I expect all of you that are taking it to get a minimum of a 3, just by being here in this class. Okay? You will. You will very, no, guys.
You'll never find out.
If you know me, you should know that answer. Okay?
We all get like.
Your value is not in a score or a number. Your value is in you as a person.
Yeah. When we all failed. Yeah, when we all failed that one test. And he was like,
If you all failed, then I failed. So,
Remember the Impossible Lab?
Oh my gosh, I've never hated anything more.
which
in my
one?
life.
Oh, that was fun.
I
You
love
had to like
that.
mix this stuff and you didn't know
We
it.
had 12. We had 12.
Oh, yeah.
No, I like that one.
That's the worst thing
I
ever.
Yeah.
hated that.
All right,
I got her.
That was my.
let's keep going. Thank you for derailing us, Grady. Appreciate that. A 200-gram piece of silver wire. As soon as we get locked, we just unlock. A 200-gram, yeah, I know. 200-gram piece of silver wire is found wound into a coil, dropped into water, and a calorimeter at 25 degrees Celsius. Final temperature is 51.4. Calculate the initial temperature of the silver wire. Assume the heat transfer is complete. The specific heat of silver is 0.235. For water, it's 4.184. What would be the first thing you'd solve for here? The specific heat. No, first you'd solve for the Q of the what? Water. So I'd solve for Q water, which would equal SM triangle T. So QW equals 4.184 joules per gram degree Celsius times the mass of water, which was what? 270 grams. Because we know that water is 1 to 1. Water's density is 1. Probably should have technically said distilled water. Times change of temperature. It went from 25 to 51.4. So what is that? 26. What? 26.4 degrees Celsius. Okay. So QW equals what? Let's not round. Let's just do like to the nearest whole number.
You could probably play it on that. On the boom one.
Oh yeah, come on there. No, get the.
Huh?
You have to have like all of them.
So you like
I bet we could. Missing notes, man.
I got 22,865. Let me check.
Oh, we got double calculators going here now? Are you kidding me?
Kidding me, Derek.
No, we got hella fun jobs.
Derek is not
We already have 2 XP.
29,823.
For the Lord.
Yeah, no, you have it though.
For the
Are
Lord.
we good now? Are we done? I can't see that. Are we done calculating?
Yeah. 29,823.
Question about the equal test.
Yes.
What calculators are we allowed to use on the test?
Well, Desmos, and then I think just a graphing calculator. I believe so.
So like the one that Mr. Brown has?
I think you could Google it quick. Lucy, will you Google that for us? I'm pretty sure you can. All right. So this is asking for the initial temperature of the silver wire. So this means that Q water equals negative Q water equals Q. Yep, it doesn't really matter if you make it negative positive, right? So I'll say that 29,823 joules equals, that's my Q, 0.2. Thank you.
Whoa, I thought you were laughing at it.
There's my specific heat of my metal times the mass of the metal, which was 200 grams, times triangle T. I'm solving for triangle T, yes? Someone do this calculation with me. Divided by 0.235. What?
Are you ready? Are you ready for the list?
I got 634. Yes? Triangle T equals 634. But that's not the answer they're looking for. They want to know, what's the final temperature of the water? No, wait. Oh, the initial temperature of the silver wire. So,
You have to subtract 25 degrees Celsius.
Shouldn't it be negative?
Cindy, stop making me uncomfortable.
I'm trying to find out.
Shouldn't you have made the negative?
I should have. But what you guys need to know is you have to add, right? Yes? Because the wire should have cooled down. Yes? Right? So I need to add this to my initial temperature. What was my initial temperature of the wire?
Regular,
25
right?
degrees Celsius.
We have to assume
Room temperature?
we have the final temperature of the water, which we assume is the final temperature of the metal, right? So I have to add that to the metal. So plus 51.4. So that gives you 685.4 degrees Celsius. Okay.
Answer the question about the calculator.
What is the answer?
Scientific calculator or graphing calculator, built-in Desmos graphing calculator, your Blue Book, and Bohr function calculator.
There you go.
Allowed but not recommended.
What?
Not recommend.
Probably the bad.
It's because you don't, it's too much,
Yeah.
is why.
No, I thought it's the.
You want to determine the amount of energy in a 50-gram serving of your favorite corn. Using a calorimeter that your amazing chemistry teacher has made, chips were placed into a metal weigh boat and set on fire beneath a soda can. We used to do this lab with General Chem. Containing 75 grams of water, the water in the soda can started at 22. When chips were completely burned, the temperature of the water was 91.5. Are we good with specific heat? Yes? Yes? We've done about 1,000 of these. Do we need to keep going on this? Okay. What would be a source of error here, though?
It's not 100%.
What?
Like you spilled something.
So you're heating a pop can, right? I would say not all of the heat went into the pop can, something like that. So something about heat transferred somewhere else. Yes, Haley?
I don't know the source of error, and I'm just like, can't like relate it philosophical. Like, what if it's heat and it like pulls their heartstrings? Like they start crying.
But we'll enjoy reading it.
All right, that's it. Sure, it was. If I don't know how to do anything, all right.
The term enthalpy is used to describe the what exchange? Heat. The symbol for change in enthalpy is delta what? Delta H. To the right is the phase change diagram of a pure substance, also known as a
Oh, that was like on.
STEPI. CP Chem did these today. It's kind of funny that we're doing a STEPI today. I should send a picture of this to Silvaji. She would appreciate this. Okay. To the right is a phase change diagram where a pure substance. Label the following: solid, liquid, gas, melting, vaporizing. Where's my solid? Liquid, gas, melting, vaporizing. And if you're going the other way, what would be on the other side of this? condense, or freeze/solidify. Yep. What is the approximate melting point of this substance? What would you guys say?
Melting point, like 38.
38. Sure, 35. Boiling point?
60.
62. Okay. Why does the temperature stay at 60 for so long? This is a good question. The energy being put in, we did this freshman year. All right. Why does the temperature stay the same during a phase change? The energy in is equal to what?
Energy out.
Mm,
Okay.
the amount of energy to break. Be careful here. Am I breaking bonds? To break the intermolecular hydrogen bonding. You could have just said intermolecular forces, but let's be specific because we know that this is water. Hello. Yes, I can. Thank you. Lucy, could you take the clapper and the box of stopwatches to Mr. Knight? Clapper, box of stopwatches to Mr. Knight. Yes. That's it, right there. The wood thing, yep.
She's going for the.
And the box of stopwatches. Thank you. For this substance, which state of matter has a higher specific heat, the solid or the liquid phase?
Has a higher.
Which one can hold heat in better? Do you have the stopwatches? Yes. Which can hold heat better? Solid. Why? Particles are closer together, right? Solids, because there's going to be particles closer together. Also, you could also look at the slope, right? Label the equation locations on the graph where you would use this equation to calculate heat. Q equals SMAT. That's going to be triangle T, right? Triangle T, triangle T. And where it's flat, the way I taught this, it's stoic, right? Stoic, because stoic goes left to right. Do we need to do the calculation for step B? They're not going to make you do that on the AP test. No. It's too specific on one thing. Too specific. All right. Flip it. Complete the chart for each of the following physical processes. Endo or exo. Here we go. See what I did there? Vaporizing, endo or exo. Have we already done this? Endo. Positive or negative delta H? Positive. Condensing. Exo. Positive or negative? Negative. Freezing. Exo. Negative. Melting. Endo. Positive. The following information is about substance B. Complete the table. Delta H to melt is 25, to boil is 58. What about to condense? Negative 58. Kilojoules per mole. To freeze? Negative 25 kilojoules per mole. It's in the box with the stopwatches. Flip the page. Is this the right page?
This is like the dumbest question.
That's probably Mr. Knight telling me to tell me that he found it. Yes. You found it in the bottom of the box? All right, great. Thanks. Huh? Yeah, it's fine. I heard him yelling down the hall as I was like on the phone. We found them. How does Q relate to H? I'm on the wrong page. I'm on the right page?
Yeah.
Okay. How does Q relate to H? What would you guys say?
They're direct.
They're pretty much the same, but they're a little bit different.
Because one time someone sat
Q
down
is
and
just
thought to come
joules,
up
right?
with all of
But
this.
Q I would say is equal to the heat transferred, right? Because it's that triangle T. Whereas your delta H is more about your overall potential energy, right? Yes? So delta H you're getting from the graph. Q is more about the heat transferred. So change of potential energy, heat transferred.
And isn't, because delta H is per mole too, right?
Yep,
That's, yeah.
you got it. The delta H of the reaction, A plus B yields AB is 3401 kilojoules per mole. What does this mean? Write it out in your own words. So a first year chemistry student would understand. What does this mean? The delta H is positive.
Positive.
So for those two things to combine, it takes heat.
For those two things to combine, it takes 3,401 kilojoules per mole of reaction. Because what if it was 2A? And it was asking for A. What would I have to do to this number? Divide by 2. Yes. Okay. Consider the following reaction. How much heat would be absorbed or released for the decomposition of 10 grams of NaOH? Take 2 minutes and do it. Take 2 minutes and actually do it. This would be a good one to do. I will hydrate. What do you guys calculate? 39.997 is NaOH's molar mass. 39.997. I have a lot of them memorized. Water is 18.15. CO2. I got a lot of them. Also from mixing chemicals, you got to know your molar mass to figure out your molar ratio.
Right.
Did you win yesterday?
Yeah, it was. The diamond is not.
But that was the hard one, right?
No, the harder ones.
Okay.
The diamond is not great.
Oh, that was it.
Wait, did you do this?
Oh, no, I didn't.
I'm going to start my work. 10.0 grams NaOH times 39.997 grams NaOH. 1 mole NaOH times 2 moles of NaOH for 1 mole of reaction. For every 1 mole of reaction, I get negative 568.98 kilojoules. Did your work look something like that?
Would you need that Stoic step to get it right?
What's like step?
The moles of NaOH to moles of reaction.
If you don't have the 2, you're not going to
No,
get it
I had
right.
the 2. I just did 2 moles of that to the heat.
Sure. That's fine. Remember, show work. Would I know what you were doing if you didn't have the last step? Yeah. All right. What'd you get?
Negative 71.1.
Negative 71.1 kilojoules. Would that be absorbed or released? Released. Release. Flip the page. We're moving. We are like legit. How much more? Is this it? 5 to go? Really?
Is that including back and
All right, here we go. On the amino acid to the right, label the amount of energy it takes to break each bond. So I've got these written down for you. You're going to need to know this. This is 390. N to C is 293. H to C is 414. C to C. C double bonded O is 730. This is OH is 464. And C to OH is also 464.
About C to C.
Yeah, I'm not sure about that. I don't know what the point of that was.
Wait, what is C
Love
to
it.
C?
I don't have that one written down.
Okay.
But I'm trying to figure out why we just did that.
Well, because it asks next to solve for how much.
On this one? But this is a different equation. That's fine.
We do. It's a good
Same
learning
amount it takes to break it down.
Let's draw our dot structure first. I've got C, Cl, 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 plus HOH, HOH, double bond, two lone pairs, yields carbon dioxide, double bond O, 1, 2, 3, 4, 1, 2, 3, 4, plus HCl, 1, 2, 3, 4, 5, 6, HCl, 1, 2, 3, 4, 5, 6, HCl, 1, 2, 3, 4, 5, 6. So, we don't have all the numbers, but let's just talk through how I would figure out how much energy is required or released to break the bonds. First of all, am I requiring energy or releasing energy to break bonds? Requiring. What bonds and how many would I have to break on my reactant side? How many C to Cl bonds would I have to break? I'd have to break 4 C to Cl bonds, right? What else would I have to break?
4 H2O.
I would have to break 4 H to O's. Agreed? Yes? And you would need numbers there, right? 4 times a number, add them up. How much energy is released to form the bonds? So first of all, are all of these bonds new? On the right? Yes. So I would be forming how many C double bond O? 2 of those. And how many HCl's? 4 H to Cl. You'd have a number with those, and you would add them up. What? Because I messed up. There we go. So, remember, the main thing is, it's products minus I just messed up. It's reactants. This is the big thing I was trying to get across. This is the only thing that's reactants minus products is bond energy. So don't forget that. Bond energy is the only thing that is reactants minus products. This is exothermic if you would have calculated it. Okay. Circle the energy profile to the right that most closely matches the change in enthalpy of the above reaction. It's exothermic. Which one is it going to be? First one. My goodness, so popular. Hello. I do. I can do that. Thanks. Haley, need to go to the office. Flip the page. You guys are so mature. Okay. Here we go. Use the large delta H in the left column to label each part of the symbol. Okay. Really? Well, we know that delta is what? Change. H is enthalpy. What does a little zero mean? Standard conditions, which are what? 298 Kelvin and 1 ATM. And what's F?
Final
Formation.
formation.
That's it. Okay. Oh, I just gave you the standard conditions. 298, 1 ATM. Okay. Which method of calculating the change in enthalpy is more accurate? Using enthalpy of formation or bond enthalpy? This is tricky. I don't know how you would actually know this. I'll just tell you. It's going to be your delta H Here's why. The bond energies are just averages. It's really difficult to calculate the actual bond energy of one because the electrons are always what? Always moving, spinning, right? There could be resonance. So really your delta H is a better way to calculate it. So using the information below, calculate the enthalpy of the reaction, show your work in the box below. So I mean, I feel like we can do this, right? We can do products minus, this is now we're back to products minus reactants, right? You could do this times that plus this times that minus that plus that plus that. Yes? Okay, good. Good. Okay. Rewrite the following reactions so that it is reversed. Okay. So, if I reverse this, what do I do to my delta H? It becomes positive 37 kilojoules. Rewrite the following reaction so it is halved. What would I do to delta H? Divide by 2. Below is a hypothetical reaction. Here it is. I'm glad that we skipped that last one. The table shows all the reactions that go in the reaction above. Determine the net enthalpy for the reaction. Show your work. Do you guys remember Hess's law?
Oh, brother.
Yes?
Yes. I remember it. Hard to do. Yes, I remember it.
Do we need to do this?
First one on reaction is reversed.
So I've got AB2, right? So the first reaction, what do I have to do to it? So I have to make this AB2 yields A plus 2B, which makes that 81.3. I flipped that. So now I've got AB2. I need 2 C2D. So I'm going to skip that for a second because I've got that on both sides. I need ACD2, which is, that's weird. Why did they flip that?
Is this so fun?
It's the same thing.
Oh, yeah.
I'm guessing it was just a formatting error, but let's use it. So this one, we're going to leave that, right? Because it's on the right side. So I'd have AD plus C2D yields ACD2. I'm going to leave that as negative 253.2. I should put a check mark by the ones we've used. And then I need B2D2 on the right. Sounds like R2D2. So at reaction 5, I have to do what? Flip it. So I'm going to have 2BD2 plus C2D yields B2D2 plus 5 halves D2. So here's my B2D2. Here's my ACD. And did I flip that one or leave it? I unflipped it. I did not flip it. So it's negative 2181. Positive 2181. So do I have 2 C2Ds?
Yeah.
Yes, I do. So that's good. Right there. I have AD. Do I want AD? No. I need to get rid of that. What's going to get rid of AD? Reaction 3. Is AD on the right side of that?
Yeah.
Sure is. So A plus 1/2 D2 yields AD. So I've used this, which is negative 436.2. So that AD is gone. And then I need to get rid of some other things. I have A here. Do I have A on the other side to get rid of that? That's gone. I've got 2 BD2, right? I have 1/2 D2 over here. Yes? Where's my B's? I have 2 B's on the right. So I need to, what am I have to do to this one? Times 2. So 2B plus 2D2 yields BD2, 2. And what do I have to do to my delta H?
2. What's the sign? No, times 2.
Negative 511.5. I'm trying to think. We multiply that by 2, right?
Yeah.
Yes. But you don't multiply your half. I was thinking half reactions, your half cells. So that should cancel everything out. 2 B's is gone. 4 halves plus 1 half is 5 halves, right? 2B to T, 2B to T, you'd add them all up, you get your answer, right? Okay. Next page. Last page. We did it, guys. We did it. Before frost, it helps to protect fruit from freezing. You spray it with water, all right? Why do you spray your oranges in Florida with water? Why?
Because they're undergoing phase change.
Okay. And what does water do when it freezes?
Gets rock hard. Yeah, like the stays out.
It releases heat, right? When freezing. Because freezing is exothermic. So if you spray an orange with water and that water freezes, where's the heat going? Into the orange. That's why they spray crops with water before a freeze. Oh, by the way, that's exothermic. In the box to the left, the circle around the orange is a layer of water. Use arrows to show the heat. Wow. So the water's going in, right? And then layer of water undergoing freezing. Use arrows to show. Okay. Great. Soccer player twists their ankle. Trainer grabs an ice pack. This one, the bag is applied to the player's ankle. How is the heat going? This would be what? Endothermic. Be endothermic because the heat in the ankle is going to the what? To the bag. Yes. And that was Unit 6.